Hello and welcome to your favorite Shridevi Classes YouTube channel, where we inculcate interest and confidence in science and engineering subjects. Today in our playlist of class 12th physics, in our subject electrostatics, we'll study calculation of potential and potential difference when we are given details of existing electric field or there exist few charges in a certain configuration. Today we will also discuss some very important questions which are usually asked in different competitive exams. So let's start calculation of potential and potential difference when either electric field is given or some charge configuration is given. A source charge of positive 20 microcoulomb is placed at horizon in this coordinate system, and there are two coordinate position, A having x coordinate 5 and y coordinate 0, and another point B with xy coordinate 3, 4. We have to find out amount of work done in moving a negative 0.3 microcoulomb charge from position A to position B in the electric field of this point source charge. Now to find out work done, we have to find out potential difference, and to find out potential difference we have to find out potential of individual points A and B, and for that we have to find out the distance of test position from source charge. So for A position, the distance RA is straightforward from visual inspection, it comes as 5 mks unit meter. So electric potential at A position is kq by RA. K is 9 into 10 power 9, source charge is 20 microcoulomb, and the distance is 5 meter, and the calculation will result in 36 kilovolt or 3.6 into 10 power 4 volt. Similarly, for position B, the distance of source charge from position B, RB, can be obtained as OB by Pythagoras calculation. This x coordinate is 3 and y height is 4, and Pythagoras calculation will result as OB distance again 5 meter. So the potential of B point with the same charge and same distance is again 3.6 into 10 power 4 volt. And to find out potential difference between two positions, the potential of second and potential of first position is subtracted. The two equal identical values when subtracted results in zero value. So in zero potential difference, whatsoever positive or negative or amount of charge is moved, the total amount of work done is zero. These two A and B points are of same potential. This could be explained. Let's assume that this A to B movement is on this circular periphery. So everywhere on this circular periphery, electric field as shown by this blue arrow is radial outward for this positive test charge, and for these circular tangential positions the displacement and direction of force got 90-degree angle, so amount of work done is 0. So if we move this charge on this circle for any number of orbits, the total amount of work done will always remain 0. Whether I move this charge A to this opposite position A dash, the work done is again 0. Work done in moving a small q charge around this source charge capital Q in a circular path is always 0, because circular path got identical distance from source charge, and at same distance potential is everywhere the same. So this surface become an equipotential surface, and on equipotential surface potential difference is 0, so work done is 0. So in path A, D, C, work done is 0 because potential of A and C is the same, and potential difference between A and C is 0. Similarly, if we move charge Q from A to B, or in other path we move charge from C to B, in both conditions path got different length or positions, but the end point is same, and initial point which are different got same potentials. So potential difference between potential of B and potential of A, or potential of B and potential of C is same. So with similar potential difference, the work done in moving this Q charge along AB path and along CB path would be the same. A positive source charge of 8 millicoulomb is situated at origin of three-dimensional plane, and we have to calculate work done in moving a small negative 2 nanocoulomb charge from position P having coordinate 003 to position Q having coordinate 040, both coordinate are in centimeter, through a path which passes through 0.6 centimeter and 9 centimeter coordinate point R. Now in electrostatics, charges produce conservative field where work done in moving a charge doesn't depend upon the path, and work only depends upon initial position and final position in electric field. So here this intermediate point location of point R 069 centimeter is irrelevant in work calculation, and work done in moving a small q by a potential difference of delta V between final and initial positions is given by product of charge and potential difference. Here potential difference is difference of potential of final point Q and initial point having coordinate 0, 0 and 3 cm centimeter in this source charge 8 millicoulomb. Now the initial point P got a distance 3 centimeter from origin. So electric field of capital Q charge at R distance given by this relation, K is 9 into 10 to the power 9, source charge is 8 millicoulomb, and the distance of initial point is 3 centimeter converted into meter. Calculation results in 24 into 10 to the power 8 volt. Similarly, the final point coordinate Q got a distance 4 centimeter. So at 4 centimeter distance converted into meter, the electric field of source charge capital Q 8 millicoulomb is given as 18 into 10 to the power 8 volt. The potential difference is difference of potential of final point and initial point, and so when charge from position P is shifted to Q, the potential difference is difference of potential of final point and initial point, and it is minus 6 into 10 to the power 8 volt. And in this negative potential difference, when negative test charge of minus 2 nanocoulomb is moved, the work done Q delta V is positive 1.2 joule. And it is also true when we shift a negative charge from high potential to low potential in the direction of electric field, the negative charge will experience a force opposite to our movement direction, and external agency has to do positive work in such movement. This concept that in electrostatic field work done in moving charge or calculation of potential difference between two positions in electric field doesn't depend upon the path followed for the movement, because electrostatic field is conservative in nature. So work done calculation or potential difference calculation can be done on the basis of initial and final position of that movement, and these examples will use that concept. Here we have to find out work done in moving a charge from A to B, then to C, and finally to D, and total work done is to be calculated. Now this movement of initial and final position D is along electric field EX. So the work done in black ABCD path or this red AD path would be the same, and the Q charge will have a force in the direction of electric field QE, and with D displacement, amount of work done by electric field is QED, and work done by external agent in this case when charge is moving by itself in the direction of electric force is negative. So work done in ABCD path is minus QEXD. Similarly, in this electric field which is uniform and directed in X directions, we have to find out potential difference between position A and B. The coordinate of A in meter unit is 34 and that of B is 50, and in place of this black movement we follow a path A to M and then M to B. The work done in both paths would be the same, but here from A to M the movement path is perpendicular to electric field, so potential difference along AM path is 0. Potential of A and M would be the same, and between M and B the displacement of 2 meter along electric field direction will need 2E potential difference, and this potential difference is negative because electric field is directed from high potential to low potential and we are moving from high to low in the direction of electric field, so it is minus 2EX potential difference between A and B. Similarly, in this uniform electric field which is directed in Y direction, for the same 34250 movement AB, we make movement along electric field direction and perpendicular to electric field direction. This 2 meter movement perpendicular to electric field won't involve any work done or potential difference. Potential of M and B is the same, but here movement of unit positive charge from A to M against electric field or force direction require work from external agency, and this work is 4 EY for 1 unit charge, and this would be the potential difference between A and B. And in similar type of question, when the electric field is produced by a point charge, then 3-4 position and 5-0 position got similar 5 meter distance from source charge, so potential of A and B is the same, so potential difference between A and B in this case would be 0. So calculation of potential difference in the electric field of point charge and in uniform electric field got different practices. For point charge we have to find out potential from KQ by R relation, and potential difference will be obtained by as difference of two potentials, and in uniform electric field we have to make path along and perpendicular to electric field. Perpendicular path doesn't involve potential difference, and along path will give you potential difference very conveniently as product of electric field and displacement. Application of superposition principle for electric electric potential calculation is quite convenient. Potential at a point due to presence of several charges is very simple. It is simple scalar algebraic sum of all individual potential contribution obtained by considering only one charge source at a time. And in such calculation, there is no need to do complex vector like summations. As in these example, if we have a equilateral triangle, square or pentagon or any other regular polygon and each vertex got uniform charge at vertices, then if we take electric field contribution calculation at symmetrical center position, we found that as in this square, contribution of A charge, contribution of charge placed at C are equal and opposite will get cancel out. Similarly, contribution of electric field from B charge and contribution of electric field from charge placed at D position get cancel out. So in a regular polygon, resultant electric field at symmetrical center is 0 in square, as well as in this triangle, electric field of A charge, B charge, C charge make a symmetrical equal magnitudes, and resultant of these three would become 0. Similarly, this could be said for pentagon, hexagon and or any other regular polygon. But for potential calculation, positive charge contribute positive potentials, and if each vertex got center distance small x, then the resultant field could be obtained as summation of charge of all vertices. Say for example, in this triangle it is 3kq by x, for square it is 4kq by x, and for pentagon it is 5kq by x. For different nature of charge distribution, there is no definite relation between zero or non-zero values of electric field intensity and potentials. All type of combinations are possible as per the condition of charge distribution. As in this square, all vertex got identical charge, then resultant electric field vector sum is 0, but resultant potential is 4kq by x non-zero. Whereas in this case, opposite polarity charges produce opposite directed electric field and will get cancel out. Similarly, electric field of this negative charge and electric field of this negative charge are equal and opposite will cancel out. So resultant electric field at center position for this configuration is also 0. But in this case, if we take summation of charges at all vertex, that is again 0. So the potential is also 0. So in this case, there is only electric field which is 0, but potential was not 0. But in this case, both electric field intensity and potential at center position is 0. In this case, electric field of this positive charge and this negative charge both acts in the same direction. Similarly, electric field of this positive charge and this negative charge both act in the same direction, and these two equal vector produce their resultant in midway of root 2 times. So electric field is not 0 here, but if you take summation of charges at all four vertex, that is 0. So the potential at center position is 0. And in this case, electric field of this positive charge and this negative charge are in the same direction, and electric field of this positive charge and this positive charge equal and opposite get cancel out, and the resultant electric field of all four charges is along this direction and non-zero, and summation q is also not 0, so potential is not also 0. So there could be all sort of possibilities depending upon charge distribution, but one relation in electrostatic is definite between electric field intensity and potential. If there is no electric field in space positions, then potential at everywhere remains constant. There won't be any potential difference, because potential difference is caused only when there exists an electric field component along that direction. Similarly, if potential is constant in space positions, we can say electric field is 0 in those positions. This certain relation between electric field intensity and potential difference is very often asked in our examination. In all conductor bodies, internal electric field is 0, so there won't be any potential difference inside the conductor or along its surface. Its whole body, all along its surface, and this inclusive all volume become an equipotential surface. So in the absence of electric field, there is no potential difference, and potential everywhere remains the same, and vice versa. If there is no potential difference, we can say there is no electric field component along that lines. Now in electric field, when we move a positive charge against electric field, external agency has to do work and potential will increase. So we can say electric field is directed from high potential to low potential. We hope that this informative learning video has improved your conceptual clarity as well as subject understanding. Now you can confidently and conveniently solve related examination question with tremendous ease and correctness. If you found this potential difference calculation video useful, do share it with your friends, and to get more from Sridevi Classes YouTube channel in terms of study material and online classes, do join our membership. Thank you very much.